Hello everyone and welcome to part 3 of lecture 13 and 14. In part 1 and part 2 of this lecture, we talked about different classifications of fire heaters. We talked about direct and indirect fire heaters, and then we looked at different construction aspects of fire heaters. In this part, we are going to talk about the operation of fire heaters, and we are going to talk about mainly about fuel combustion and the performance of fire heaters in terms of heat transfer point of view. And from the heat transfer point of view, we have two things here. So when we are using a fire heater, we are generating heat by burning the fuel, and that heat is then being transferred to the process stream. And if there is a deviation between the heat generation and heat transfer, then that gives us the efficiency of the system. Okay, so we will talk about the efficiency of the furnace as well. Two things to clarify here: that first, that we will be dealing with direct fire heaters that use radiation and convection. So we are not going to talk about other types of fire heaters from now onward. We are just focusing on fire heaters that use radiation and convection. And the second thing is that we are going to deal with fire heaters that heat the process fluid directly. Okay, so we are not dealing with boilers or fire heaters for heating of oil in order to use as a hot utility. Here we are considering fire heaters as primary hot utility. It means that the fire heaters will provide heat to the process directly. So this slide captures what we are going to talk about, and we have seen this slide before as well, that we have a furnace where we are providing the fuel and air, and then you have burning of the fuel, and as such you are generating heat, and that generated heat is being transferred to the process heat. This Q heat is actually the heat that is transferred to the process fluid, and once you are done with extracting of the heat from the flue gases, the flue gas goes to the stack and then to the ambient atmosphere. Okay, so what is happening inside this furnace is graphically represented here. So you start with the theoretical flame temperature. That will be the topic of our next video, and is essentially the supply temperature of the flue gas. And then you use this flue gas to heat up your process fluid, and as such the temperature of the flue gas decreases. And based on the shape of GCC and your pinch point and dew point, we can determine what is our stack temperature. Okay, and after the stack temperature, the flue gas enters the stack, and then we release it to the ambient atmosphere. So here you have two sort of heat. One, you have Q fuel, that is the heat generated by the fuel, by the burning of fuel in the furnace. And then you have the heat, Q heat, that is the QH min of your process. Okay, and then you have this stack loss from this point to this point here. It is the heat from the flue gas that we cannot use to heat our process, or we don't require it. But actually it is not necessarily a loss, because we can use some part of the heat from this flue gas in the stack either to heat the fuel or preheat our air. Okay, and as such we can increase the supply temperature of flue gas, and we will talk about that in the next part. So here we have, as I said, these two heats, and if because we are in energy conservation, so by that we have to have these two heats equal. Okay, so depending on how much heat you are being generated and how much heat is being transferred to the process, we can determine the efficiency of your furnace. Okay, and the efficiency of your furnace depend on a couple of things. It depends on the type of fuel that you are supplying, the air, the amount of air you are supplying, or the temperature of the air, and then you have how much heat you are taking out of the flue gas. Okay, so let's talk about some of these parameters in the next slide. In any industrial setting, the choice of fuel is driven by various factors. For example, the supply, the storage, and other environmental factors. And broadly speaking, we classify fuels in three main categories. We have the gaseous fuels, for example, natural gas, that is one of the most common form of gaseous fuels. Then we have liquefied petroleum, LPG, and now we have a new form of fuel that is still kind of not very common, but it's been considered in many different applications, that is hydrogen. We have liquid fuels that are, for example, light fuel oil and heavy fuel oil, like gasolines and diesels. And then we have solid fuels like coal, petroleum, or biomass. Okay, so there are several important properties or physical properties of these fuels that we need to consider before we choose a particular fuel for our application in fire heaters. So these properties are calorific value, density, and composition. And in the next couple of slides, when we explain these things, it will become clear to you why these parameters are important when we are selecting a fuel. So what is this calorific value? So in a nutshell, calorific value gives you the amount of energy stored per unit kilogram of the fuel. Okay, and there are two of these calorific values. You have gross calorific value or higher heat value, and then you have the net calorific value or the lower heat value. Okay, and the main difference between these two is the state of water present in the flue gas after the burning of the fuel. Okay, so here you have the quantity released after complete combustion at standard conditions in which the water is present in liquid state, while for the case of net calorific value, the water is present in the vapor state. And as such, it is very easy to relate these two because um, the net calorific value is lower than the gross calorific value by the amount that the amount of energy that is required to vaporize the liquid present in the stream. Okay, so here you can see that the lower heating value is equal to high heating value minus the mass of the condensate formed per unit volume multiplied by the latent heat vaporization. Okay, so this is the amount of energy that you need to provide to this liquid to change its state from liquid state to vapor state, and as such you are using some of the heat from the combustion of the fuel, and that is why your net heating value would be lower than your gross heating value. Okay, so let's have a look at some typical values for different fuels. So here you have provided the type of fuel, the high heating value and the lower heating value, and you are given these values in megajoule per kg or megajoule per cubic meter. Um, and if you look here that for different types of fuels, for example, for gaseous fuel, if you're using hydrogen, methane, or thing, with exception to hydrogen, you will see that the calorific values for different gaseous fuels are more or less in a similar range. Okay, so this is like from 45 to 50. Similarly, for liquid fuels, talking about gasoline, diesel, petroleum fractions, and some light and heavy oils, again you see that the range is there is a range that we can be defined. So it goes from 40 to 43 or 44, and similarly, then you have solid fuels in the low range, that is 29 to around 30. So by selecting a fuel type, you can get an idea what kind of heating value or calorific value you are going to get for your fuel. So it is very common to use gaseous fuels in our furnaces compared to the other fuel types. And if you look at the composition of these fuels, the reason become quite clear. So for the case of natural gas, you have carbon dioxide and a range of different hydrocarbons, and for the case of liquid and solid fuels, you have carbon, that is the major component of your fuel, but you also have significant amount of sulfur and nitrogen present, and you are also going to have a lot of particles generation. Okay, that is mostly common for coals. And so if you burn fuel, liquid fuel, you will see that you are going to produce a lot of SOx, and then that SOx can react to other components or to the metal itself and cause corrosion, and it can also react with hydrogen present in the system and create hydrogen sulfide, that is again a very toxic gas and cause acidic corrosion as well. And if you talk about coal, for example, you have a very similar situation. You have quite a lot of sulfur present as well, so you're going to have same problem of SOx generation as for the liquid fuels. But now you can also see that here you also have a lot of NOx and ash as well, so you are going to have a lot of particulates in the flue gas as well, and that is going to cause pollution as well. Okay, so for the case of liquid fuels and solid fuels, if you are using, then you have to treat your flue gas, and you have to take the flue gas to a scrubbing unit where you remove SOx and NOxes and these particulates in the flue gas before you can emit it into the atmosphere. Okay, and that is also going to cost you for the treatment as well. So that is why most of the time we use natural gas, because that it is going to have much lower, for example, pollutant emission. So despite the low calorific value, so because here you can say that the net calorific values are slightly lower compared to the liquid fuels, but we still prefer gaseous fuels because of their potential to have much lower pollution compared to the other two fuel types. Now let's have a look at another aspect of burning, which is oxygen supply or the air supply. The air supply to the furnace is a critical component in ensuring that the proper combustion of the fuel and the safe and efficient operation of the furnace. The amount of air required for combustion depends on type of the fuel being used and the furnace design as well. And it is quite important to monitor the air supply to the furnace regularly to ensure that the correct ratio is being maintained. So most of the time we have to supply excess air to complete the combustion in a furnace. So it is really important that we maintain a correct fuel to air ratio, because if we have too much excess air, it will cool down the flame, in the sense the furnace might not reach the temperature that is required for combustion. And as such, it is going to produce less heat, which can decrease the efficiency and increased fuel consumption. You will also increase the volume of the flue gas and the heat loss, because you are producing, or you're giving too much excess air, and as such the whole volume of the system will increase, and that is going to further decrease the efficiency of the furnace. On the other hand, if you have too less excess air, it means that you are not providing enough oxygen to complete combustion, and as such you are going to have a range of byproducts, like for example, instead of carbon dioxide you are going to produce carbon monoxide, and again, because of incomplete combustion, you are going to have low efficiency of the furnace process. So a correct fuel to air ratio is really important. And now to supply the air to the furnace, we can use a number of drafting options that we discussed in part 2, where we talked about that we can use either a natural draft, or we can use mechanical draft by using fan or blowers at the inlet or at the outlet of the furnace to supply air to the system. As I mentioned, that the excess air is normally provided to ensure complete combustion. Now, depending on the nature of our fuel, we could have a different typical value for excess air. So, for example, for the case of natural gas, LPG, and fuel oil, you can see that we require a relatively low percent of excess air, but for solid fuels like coal and wood and municipal solid waste, we need relatively much larger value of excess air. Okay, and this is again to ensure you have better mixing of the fuel with the gas, and then you have the complete combustion. So as I said previously, that the heat that is generated by the fuel will be transferred to the process fluid. So the heat will come from the burning of the fuel to get the flame, which will then radiate heat and also produce flue gas. And then that flue gas moves upward by either natural convection or forced convection, depending on what kind of drafting mechanism you are using. And then it exchange heat with the convective section and then goes out of the stack, and the temperature at which it goes out is normally decided by either the pinch temperature or the dew point or the shape of the GCC. Okay, so like we discussed in the previous lectures. In terms of the process fluid, normally you get the process fluid is moving in the opposite direction to the flue gas, so you have a kind of a countercurrent flow pattern. So the preheating of the process fluid happen in the convective section, and then it moves down to the shielding section, and then you have finally the radiant section. Okay, what I explained here can be better explained with the help of a figure. So here you have a box furnace where you have two flames for two burners here, and you're producing flame, and the radiant heat from these flames are being transferred to the tubes here. Okay, so you have very high temperature of the flame, and you have very high heat flux here as well. And then you are also producing flue gas, so the flue gas is moving upwards, and as such you have a portion of convection happening as well. So in the radiant section, the major part of heat transfer happens through radiation, but you have also some portion of convection happening as well. Okay, so as the flue gas is moving upwards, it's actually becoming cooler and cooler, and once it reaches, but still at the radiant section, it is still very hot. But then it enters the convective section, or the entrance of convective section, that what we call shielding section. And the reason we called it shield section is because, as I said, the flue gas is quite hot, and if we directly give it to the tubes, then it is going to melt the metal. So here we have kind of tubes or material that can withstand the hot temperature of the flue gas. Okay, and that's what is called shield section or choke tubes. And then some part of the heat get transferred to the process fluid here again, and then the flue gas get further and further cooler, and then you have finally the convective section where the final part of the heat exchange happen, and then finally the flue gas moves out of the stack. Okay. While for the case of process fluid, as I said, it moves in the opposite direction. So here, all these tubes, they have process fluid in it, and you have different number of passes. So here you have 1, 2, 3, 4 passes of these tubes. So you have rows and rows of these tubes, and they are going in and out. For example, they are going up, down, to have multiple passes. Okay. So the process fluid is moving in the downward direction to create a countercurrent flow pattern. So again, you have a preliminary heat transfer that is mostly like preheating of the convective fluid, process fluid. Then you goes to the shielding section where the process fluids get even further hot because of the high temperature flue gases, and finally it goes to the radiant section where you have the highest temperature flue gases and the radiant heat coming from the flame directly as well. And then you have the maximum heating here of the process fluid. Okay. Now, in terms of energy optimization and heat recovery, we need to see if our furnace is performing efficiently or not. And we can calculate the furnace efficiency if we perform a heat balance or energy balance around a furnace, so that we can see that what is coming in and what is going out, as we talked in the previous slide as well, that what kind of heat mechanisms are involved. So here we have different sources of heat and sinks of heat in a furnace. So in terms of the sources of heat, what heat is coming into the furnace, we have the heat of combustion that is being generated by burning of the fuel. Okay, then we have the sensible heat of combustion of air, and that is the heat that the air is carrying. And actually it is very common to preheat the air with the exhaust of flue gases from the stack. Okay, then we have also heat, sensible heat that the fuel can carry. So there might be a situation where the fuel is at a higher temperature than the ambient, or there might be a situation where actually the fuel is coming from the atomizer. For example, if you have a liquid fuel and the atomization can be done by steam, so it will have a lot of energy by itself before even it get burned. So we have these three main sources of energy or heat coming into the furnace. Now let's have a look at the source or the sinks of the energy, or how the energy is going out of the furnace to the process. So one is the heat transferred to the radiant section, to the tube, that is Q radiant. We talked about that in the previous slide. And then we have the heat transferred in the convective section, and the heat transferred in the convective section also contains the heat transfer in the shield section. Okay, so this convective section is the sum of convective section and the shield section together. Then we have some heat that is being lost to the environment through casing. Okay, because we always are going to lose some part of the heat to the environment because of heat losses. Then we have some part of the heat that will be taken out of the furnace with the flue gas, so that is the enthalpy of the flue gas, so that is also going to be lost to the environment. Okay, so if you perform an energy balance, you will see that we have these three sources and four sinks in the furnace. So number three here, heat sink, and number four, heat sinks, they are going to be lost to the environment, and we are not going to benefit from them. So we are not going to consider them when we are calculating the efficiency of the furnace. So to calculate the efficiency of the furnace, essentially we need to take a ratio of the heat that is gained by the process to the heat that is generated in the furnace. Okay, and we discussed this figure in the beginning of the lecture, in the beginning of this part as well, where we look at that the heat that is gained by the process is the heating requirement QH min from our GCC or from our composite curves, and that heat comes from the radiant section and the convective section, so the combined heat of radiant and convective section. While for the case of the fuel, we are getting, or we are, the total heat that is being generated in the furnace is the sum of QH min, the heat that the process is taking, plus the heat that is being lost in the stack. Okay, and this stack loss very much depend on the pinch temperature, the dew point, and also the shape of the GCC. But another factor that it depend on is the critical flame temperature. Okay, and we will talk about that in the next part of this lecture. Okay, so that is all for this part. Thank you for your time.